In the previous combinatorics videos, we were talking about permutations, which was about ordering. So the order always mattered. But in the upcoming videos, including this one, we're going to think about what if order doesn't matter. So imagine that we have 10 applicants and we're trying to fill 3 jobs, and these are 3 identical jobs. How many groups of 3 could we hire? So it doesn't matter the order that we hire them in or which slot they're getting put in. All they care about is, am I getting the job or am I not getting the job? So we would call this a combination. So let's talk about the definition of combination. If we have k unordered elements, then so let's talk about the definition of combination. K unordered elements are called a combination of size k. So let's talk about a theorem now. The number of ways to form combinations of size k from a set of n distinct objects, repetitions not allowed, is written n choose k. You could write it like this, or you can write it this way. And what it is equal to is n factorial divided by k factorial times n minus k factorial. Okay, so why is this true? Well, we have this understanding of permutations from the previous videos, so we can call on that. So if we think about k factorial times n choose k, that's the number of permutations of length k that can be formed by n distinct elements. However, another way that we could calculate that is n factorial divided by n minus k factorial. Therefore, that means that this is equal to that. So if we take k factorial and divide it over, we get n choose k is equal to n factorial divided by n minus k factorial times k factorial. Okay, so let's apply this to a couple of examples. So first example, we have ultimate Frisbee players, and they're meeting to play pickup. 14 of them show up. Now they need to split up into 2 teams of 7. How many ways can they split into 2 teams of 7? So I drew, this is like team 1, here's team 2. And since we thought about ordering before, we could first imagine order does matter and then take the ordering out of it. So order doesn't actually matter because we just care about like who's on this team and who's on that team, but it can help to calculate things maybe first by thinking about order mattering. So if we are filling up team 1 first, when we get to this very first slot, there are 14 different people we could choose from. Now we put one person into that first slot, we get to the second slot, there are 13 people to choose from. We get to the third slot, there's 12, 11, 10, 9, 8. So 14 times 13 times 12 times 11 times 10 times 9 times 8, that's equal to 14 factorial divided by 7 factorial. But that would be assuming that order does matter. So if the order doesn't matter, we would need, how many ways can we move these people around? Like if we had the people on the team already determined, how many different ways could we arrange them from left to right? And that would be 7 factorial. So we have 14 factorial divided by 7 factorial, 7 factorial. So that is equal to 14 choose 7. Okay, so we only talked about team 1, and that's it. So why does that make sense? Because once we have determined who's on team 1, then anyone who's left over just goes on to team 2. We don't have to worry about counting anything because the order doesn't matter. All right, next example. We have 5 members of the Board of Trustees convening, and they are all shaking each other's hands. How many handshakes are going to happen? So of course, each handshake only involves exactly 2 people. So the number of handshakes is going to be 5 choose 2, which is 5 factorial divided by 2 factorial times 3 factorial. And we can simplify this out since these numbers aren't too big. It would actually make sense to crunch this number out. So 5 factorial is 5 times 4 times 3 times 2 times 1. 2 factorial is 2 times 1, or just 2. 3 factorial is 3 times 2 times 1. So now we can see the 3's are going to cancel, the 2's cancel, the 1's cancel. So we have 20 divided by 2, or 10 handshakes. Okay, next example. We have 7 potential people to put on a panel, but we can only fit 4 people on the panel. So we want to create a 4-person panel from a pool of 7 potential panelists. How many different panels can we make? There are 7 people. We're choosing 4, so we have 7 choose 4, which is 7 factorial divided by 3 factorial times 4 factorial. Again, we can write that out. Cancel some stuff. 3 times 2 is equal to 6, so we can cancel that. So we end up with 7 times 5, or 35. So we have 35 different panels that we could make.